You've been lied to since you were a kid. The sun isn't just a giant ball of fire floating in space. If it were fire, like the flames we see on Earth, it would have burned out in just a few thousand years. And yet it's been burning for over 4.5 billion years. So how is that possible? The truth is, the sun isn't fire. It's something far more powerful and far more terrifying. It's a cosmic nuclear engine, fusing atoms together to create endless energy. This is how the sun actually shines. Let's start with something basic. Fire, as we know it, needs oxygen. The sun has no oxygen. So what's powering it? A process called nuclear fusion. In the sun's core, hydrogen atoms are constantly crashing into each other. When they collide at insanely high pressures and temperatures, they fuse into helium. This process releases a massive burst of energy. Not heat from fire, but energy from the mass of atoms themselves. Every second, the sun turns about 600 million tons of hydrogen into helium, and in the process, it releases the energy of 1 billion nuclear bombs every second. That's what fuels the light and warmth we feel on Earth. The sun isn't just a big glowing ball, it has layers. Each layer plays a part in how the sun works. At the very center is the core, where nuclear fusion happens. Temperatures there reach over 15 million degrees Celsius. Above that is the radiative zone, a dense region where energy takes tens of thousands of years to move outward. Next is the convective zone, where hot plasma bubbles upward like boiling soup. The surface we can see is the photosphere. That's where visible light comes from. And beyond that, surprisingly, is the corona, a super-hot outer layer that can reach over 1 million degrees Celsius. It sounds backwards, but that's the sun, full of strange extremes. So how does nuclear fusion actually work in the sun's core? The sun's mass creates enormous gravitational pressure, about 265 billion times Earth's atmospheric pressure at the core. At these conditions, hydrogen nuclei get compressed to densities 150 times that of water. Here's the physics. Hydrogen nuclei naturally repel each other due to electromagnetic force. But when temperatures reach 15 million degrees Celsius and pressures become extreme, the nuclei move fast enough to overcome this repulsion through quantum tunneling. When two hydrogen nuclei finally fuse, they form deuterium, releasing a positron and a neutrino. The deuterium then fuses with another hydrogen to create helium-3. Two helium-3 nuclei eventually combine to form helium-4, releasing two hydrogen nuclei back into the process. This is called the proton-proton chain reaction, and it's remarkably efficient. The mass difference between the reactants and products gets converted to energy according to Einstein's E equals mc squared. Just a tiny bit of mass creates enormous energy, about 26.7 MeV per helium nucleus formed. We've been trying to replicate this on Earth for decades. Our tokamaks and stellarators can achieve the temperatures, but maintaining stable plasma containment remains challenging. The sun does this effortlessly because its massive gravity provides natural confinement that we have to create artificially with magnetic fields. The sun's magnetic field is incredibly complex and dynamic. Generated by the movement of charged plasma in the convection zone, these magnetic field lines can become twisted and tangled over time. When magnetic field lines with opposite polarities reconnect, they release stored magnetic energy in explosive events called solar flares. These can release energy equivalent to billions of atomic bombs within minutes. Coronal mass ejections are even more dramatic. They hurl billions of tons of plasma into space at speeds up to 2,000 kilometers per second. When this charged particle stream reaches Earth, it interacts with our magnetosphere, potentially causing geomagnetic storms. The 1859 Carrington event was the most powerful geomagnetic storm on record. Telegraph systems worldwide failed, with some operators receiving electric shocks and telegraph wires sparking. Aurora were visible as far south as the Caribbean and Hawaii. Modern technology is far more vulnerable. A Carrington-level event today could damage power grids, disrupt GPS satellites, and cause widespread communication blackouts. The economic impact could reach trillions of dollars. Scientists monitor solar activity using spacecraft like the Solar Dynamics Observatory and the Parker Solar Probe, which helps us understand these phenomena and predict space weather patterns. Let's examine a hypothetical scenario. What would happen if the sun suddenly disappeared? Light from the sun takes approximately 8 minutes and 20 seconds to reach Earth, so we'd continue receiving sunlight for that duration before realizing anything had changed. Without the sun's energy input, Earth's surface temperature would drop rapidly. Within a week, global temperatures would plummet to around -73 degrees Celsius. The atmosphere would begin to freeze, with water vapor condensing out first, followed by other gases. Ocean surfaces would freeze within weeks, though the deeper ocean waters would retain heat longer due to thermal inertia. Photosynthesis would cease immediately, breaking the foundation of most food chains. Interestingly, some life might survive near geothermal vents and volcanic activity, where chemosynthetic bacteria derive energy from chemical reactions rather than sunlight. These ecosystems exist independently of solar energy. The scenario illustrates how fundamentally dependent Earth's entire biosphere is on continuous solar radiation, not just for warmth, but for driving weather patterns, ocean currents, and the entire photosynthetic process that sustains most life on our planet. The Sun represents one of nature's most remarkable nuclear reactors, a self-sustaining fusion engine that has operated continuously for 4.6 billion years. Through the proton-proton chain reaction, it converts approximately 600 million tons of hydrogen into helium every second, with about 4 million tons of matter converted directly into energy. This process powers not only our climate and weather systems, but the entire foundation of life on Earth. The Sun's influence extends far beyond simple heating. Solar radiation drives photosynthesis, creates wind patterns, powers the water cycle, and generates the magnetic field interactions that create phenomena like aurora. Every calorie of energy in our food chain ultimately traces back to solar fusion. Understanding stellar physics has also advanced our knowledge of nuclear processes, quantum mechanics, and plasma physics. The same fusion reactions powering the Sun could potentially provide clean, abundant energy for human civilization. For the next 5 billion years, our Sun will continue this nuclear dance, gradually converting hydrogen to helium until it eventually exhausts its fuel and evolves into a red giant. Until then, it remains the most important star in our cosmic neighborhood, the engine that makes Earth a living world.